Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this video we are going to solve example problem 9.3, chapter number 9, gas turbine cycles, from the book Applied Thermodynamics by Eastop and McConkey. Statement of the example problem is: a gas turbine unit takes in air at 17 degrees centigrade and 1.01 bar, and pressure ratio is 8/1. The compressor is driven by a high pressure turbine, and the low pressure turbine drives a separate power shaft. The isentropic efficiencies of the compressor and the high pressure and low pressure turbines are 0.8, 0.85 and 0.83 respectively. Calculate the pressure and temperature of the gases entering the power turbine, the net power developed by the unit per kilogram per second, mass flow rate, the work ratio and the cycle efficiency of the unit. The maximum cycle temperature is 650 degrees centigrade. For the compression process, take specific heat capacity at constant pressure 1.005 kilojoule per kilogram per Kelvin, and gamma is 1.4. For the combustion process and for expansion process, take the value of specific heat capacity at constant pressure is 1.15 kilojoule per kilogram per Kelvin, and gamma value is 1.333. Neglect the mass of fuel. So first of all, we will write the given data. We have given that initially, if we look to the schematic of the gas turbine unit while using the power turbine, so initially air enters at state 1 and it leaves the compressor at state 2. This C stands for compressor. This is the combustion chamber, this is the high pressure turbine, and this is the low pressure turbine. So air enters to the compressor, that is T1, and it is 17 degrees centigrade. So converting it to Kelvin, we will add 273. It will become 290 Kelvin. And the pressure is 1.01 bar. 1.01 bar. Pressure ratio across the compressor, which is P2 by P1, and it is 8/1. Compressor is driven by the high pressure turbine. This high pressure turbine drives the compressor, while the second turbine generates or develops the power, which is coupled with the generator. So in this case, we can say that the work of the compressor, which is required for the driving of the compressor, it will be equal to the work of the high pressure turbine. Also, the isentropic efficiencies of the compressor is 0.8. High pressure turbine isentropic efficiency is 0.85. Isentropic efficiency of the low pressure turbine is 0.83. Also, we have given the maximum cycle temperature which is 650 degrees centigrade. The highest temperature is after the combustion chamber, that is T3. If we look to the TS diagram, so in this cycle T3 is the highest temperature and it is equal to 650 degrees centigrade. So converting it to Kelvin, it will become 923 Kelvin. Similarly, the value of specific heat capacity at constant pressure for compression is 1.005 kilojoule per kilogram per Kelvin, and the value of gamma, which is the adiabatic index or ratio of specific heat capacities, is gamma and it is 1.4. For combustion and expansion process, we will take the value of Cp as 1.15 kilojoule per kilogram per Kelvin, and the value of adiabatic index is 1.333. We have to neglect the mass of the fuel. So first of all, we are required to find the pressure, temperature of the gases entering to the power turbine. So this LPT, low pressure turbine, is basically the power turbine. So we will find the temperature T4 and P4 of the gas which is entering to the low pressure turbine. On the other side, if we look to the TS diagram, so this is basically the point on which we will find the temperature and pressure. So we are required to find the temperature and pressure. Pressure P4 and temperature T4. Also the net power developed, W dot net, this is the net power developed per unit mass flow rate, work ratio, and the cycle efficiency of the unit. So these 5 terms are required to calculate in this problem. So for this we will need some expressions. These are the expressions which we will use for the solution of this problem. Some temperatures are given while some are unknown. We will find those temperatures. Also some pressures and pressure ratio are given and others are missing. We will find those missing pressures as well. So coming to the solution of the problem, we will first use this expression T2S by T1 is equal to P2 by P1 power gamma minus 1 by gamma. So I am directly writing that expression. In this expression, T1 is known, pressure ratio is given, we will find T2S. So T2S is equal to, directly putting the values in this expression, T1 is 290 Kelvin. So 290 into pressure ratio is 8 by 1. So 8 power, gamma is 1.4, 1.4 minus 1 were 1.4. So simplifying this, the T2S value comes out 525 Kelvin. Now using the expression of the isentropic efficiency for the compressor, this one, to find the value of T2. So I am directly rearranging the expression and putting the values. So for that, T2 minus 290 is equal to 235 by 0.8. So rearranging this, T2 is equal to 584 Kelvin. Now work of the compressor, meaning that work input to the compressor can be calculated now very easily, because work of the compressor is equal to Cp into T2 minus T1 as mentioned here as well. So putting the values, the value of Cp is 1.005 and the value of T2 is 584 Kelvin and T1 is 290 Kelvin. So simplifying this, the work input to the compressor is 295.5 kilojoule per kilogram. This work is provided by the turbine, and it is given in the problem as well that a high pressure turbine operates the compressor. So work of the compressor is equal to work of the high pressure turbine. Now using this concept that high pressure turbine work is equal to the compressor work, so we can write that the work of the high pressure turbine is equal to Cp into T3 minus T4. If we look to the TS diagram, so this is the work developed by the high pressure turbine, T3 minus T4. In terms of temperatures, we can calculate the work of the high pressure turbine and we will use the values of T3 and T4. Similarly, for low pressure turbine, we will use the temperatures T4 and T5. So now coming to high pressure turbine work, in this expression we have WHPT work of the high pressure turbine, and it is equal to 295.5 kilojoule per kilogram. In this expression T4 is unknown, so rearranging it for T4, we can write it like this: T3 minus T4 is equal to 295.5 by 1.15. This is the value of Cp. So it is equal to, further, T4 is equal to 666 Kelvin. T3 is basically 923 Kelvin, so we will put the value of T3 first, and after this we can calculate the value of T4. So I have directly written it in simplified form. Now further, using the concept of isentropic efficiency of the turbine, this one expression T3 minus T4 over T3 minus T4s. So using this expression we can find the value of T4s. So isentropic efficiency of the turbine is equal to T3 minus T4 over T3 minus T4 S. In this whole expression, only T4 is unknown. So rearranging it for T4S is equal to 923 minus 302.5. So simplifying this, T4 is value is 620.5 Kelvin. Now using the expression T3 by T4 is equal to P2 by P1 over gamma power gamma minus 1 by gamma. This is the relationship between temperature ratio and pressure ratio for high pressure turbine. So now we can write it like this: T3 by T4 is equal to P3 by P4 power gamma minus 1 by gamma. So in this expression, T3 is known, T4 is known. We can find the pressure ratio P3 by P4. So P3, rearranging this expression for P3 by P4 and putting the values, we can write it like this: T3 is 923 Kelvin and T4 is 620.5 power. Gamma value is 1.333 over 0.333 because gamma minus 1, gamma is 1.333, and if we subtract minus 1 from this value, it will become 0.333. So the value of P3 by P4 comes out 4.9. Here in the TS diagram, if we look, so the pressure P2 is equal to P3. So P2 is basically 8 bar because we have P2 by P1 is equal to 8 by 1. So P2 will be equal to 8 bars. Directly we can say that P3 is 8 bar because P3 is equal to P2. So using this, we can find the value of P4. So as P3 by P4 is equal to 4.9, so the value of P4 is equal to 8 into 1.01 bar divided by 4.9. So I am putting the value of P1, that is 1.01 bar. Normally, if it is not given in the problem, we can directly put it as 1 bar. So it is 1.01 is equivalent to 1.00. So the value of P4 is equal to 1.65 bar. Now further we can write that P4 by P5 is equal to P4 by P3. This is the pressure ratio for the high pressure turbine into P2 by P1, because we know that from TS diagram it is very clear that P2 is equal to P3 and P5 is equal to P1. So looking to this pressure on the TS diagram, this is point 1. P1 is equal to P5 and P2 is equal to P3, because these lines which are diverging from left to right, these are constant pressure lines. So at this line from P1 to P5, pressure remains constant on this line. Similarly, on this line from 2 to 3, the value of pressure doesn't change and it remains constant. So P2 value is equal to P3. Now coming to the point, now we can write that P4 by P5 is equal to 8 over 4.9, because we know about these pressure ratios. So just we put the values of these pressure ratio, it becomes 1.63. Now using this pressure ratio to calculate further unknown temperatures, one of them is T5s. So again, using the expression of temperature ratios and pressure ratios relationship for low pressure turbine, we can write it T4 by T5s is equal to P4 by P5 power gamma minus 1 by gamma. So putting the values, P4 by P5 is basically 1.63 and gamma values 1.33, so it will become 0.33 over 1.333. So simplifying this and putting the value of T4 in the expression T5s comes out 588 Kelvin. Now further, to find the difference of temperatures required for the solution of low pressure turbine work, for that we can write the turbine efficiency, isentropic efficiency of the low pressure turbine LPT is equal to T4 minus T5 over T4 minus T5s. So we know about the value of LPT efficiency, low pressure turbine efficiency, and all these values. So the difference of temperature T4 and temperature T5 is equal to 0.83 into 666 minus 588 Kelvin. So we can write it again like this: T4 minus T5 is equal to 0.83 into 78, and further T4 minus T5 value is 64.8 Kelvin. Now we can easily find the work output from the low pressure turbine. So the work of the low pressure turbine will be equal to Cp into T4 minus T5. So we calculated T4 minus T5, directly putting the value of Cp, which is 1.15 for the expansion, and the value of T4 minus T5 is 64.8 Kelvin. So simplifying this, we get 74.5 kilojoule per kilogram. Also, to find the net power output as required in the problem, so for that net power output is equal to net work into mass flow rate. Mass flow rate in this case is 1 kilogram per second and net work is 74.5 kilojoule per kilogram per Kelvin. So the value of net power output comes out 74.5 kilowatt. Also, the work ratio is equal to net work divided by gross work. So net work is 74.5 kilojoule per kilogram and gross work is the summation of the works of both turbines. So one of them has 74.5 kilojoule per kilogram work output and the second turbine, which is high pressure turbine, it has work output and its value is 295.5. So simplifying this, the work ratio value comes out 0.201. Similarly, for finding the efficiency of the cycle, for that we will need the heat supplied as well. So heat supplied can be calculated from the expression Qs is equal to Cp into T3 minus T2. We know about these temperatures, so putting the values, Cp is 1.15 into 923 minus 584, T2 value is 584. Heat supplied comes out 390 kilojoule per kilogram. Now to find the cycle efficiency, for that we can write that it is the ratio of network output divided by heat supplied. So net work output is basically 74.5 kilojoule per kilogram and the value of Qs is 390 kilojoule per kilogram. It has also unit of kilojoule per kilogram, so they will cancel with each other. Cycle efficiency comes out 0.191, or it is in percentage, it is equal to 19.1%. So in this problem 5 things were required to find or calculate. One of them is starting from the pressure, which is the pressure of the gas entering to the high pressure turbine, and its value is, here the value of P4 is, looking to this, it is 1.65 bar. Similarly, the value of T4, temperature T4 is, looking to this, it is 666 Kelvin. Net work or net power developed is 74.5 kilowatt. Work ratio is 0.201 and the cycle efficiency is 19.1%. So this is the overall solution of example problem 9.3. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.